let's solve the first problem related to the vector space. The problem is this. Yeah, show that the set V is equal to x0, 0, y. Okay. So only two entries are there, diagonal entries are there, other entries are not there. V, x0, 0, y, whereas x and y belongs to R. That means to say that x and y are real numbers. Okay. Is a vector space over the field of real numbers R under scalar multiplication and vector addition. So you should find out whether V is a vector space. How do you find out whether V is a vector space? Very important thing is you should satisfy all the 8 conditions. Then if this satisfies all the 8 conditions, then it becomes a vector space. Okay. Yeah. This one. First, we'll take that. Let's consider a vector. See, they have given the pattern as x0, 0, y. So in order to prove all the conditions, you can consider, see, for associative law you need 3 vectors, right? That's why we are considering 3 vectors. For commutative law you need 2 vectors. So, and for maximum number of constants, how much is required is C1, C2, right, in the 7th and 8th condition. So we are considering okay, 3 constants. Okay, so let's consider vector A as x1, 0, 0, y1. Only difference is in the question they have given us x0, 0, y. You are considering A as x1, 0, 0, y1. Whereas in the B vector you are considering as x2, 0, 0, y2. C vector you are considering as x3, 0, 0, y3. Okay, so that belongs to that vector space. We are assuming that. And C1, C2, C3 are real numbers. That belongs to R. Okay, so we have to prove that ABC belongs to V. Now the first condition. Okay, what is the first condition? It's a commutative law. A plus B you have to find out. That should be equal to B plus A. Let's consider A. What is A? x1, 0, 0, y1. What is B? x2, 0, 0, y2. You add these two matrices, right? You know how to add the matrix. The particular coordinates you have to add. 1, 1 you should add with 1, 1. 2, 2 you should 1, 2 you should add with 1, 2, like that. So here x and x2 will be added. x1 plus x2. 1, 2 position you have 0, 0. So 0 plus 0 is 0. Again, the third number 0, 0 will be 0. And the fourth is y1 plus y2 becomes y1 plus y2. So answer is, after adding x1 plus x2, 0, 0, y1 plus y2. Okay. So since x1, x2 all are real numbers, right? So sum of that will also be a real number. 1 plus 2, 3 plus 5, 2 plus 2.5. Everything comes in a real number. So that belongs to V. And also you have to calculate B plus A. What is the answer you get? Is x2 plus x1, 0, 0, y2 plus y1 you will get. So even though there is a change in the position with respect to the addition, 2 plus 3 or 3 plus 2, both are one and the same. So both are equal. A plus B is equal to B plus A. Next, we are calculating the commutative law, right? A plus B plus C is equal to A plus B plus C. Now the first, I'm considering the LHS here. It is nothing but A plus B plus C. I have written B plus C in the within the bracket, right? So here it's x1. So you are going to add A plus B here, B plus C here. So x2 and x3 will be added. So resultant will be x2 plus x3, 0, 0, y2 plus y3. Then you are adding with the A, right? Final answer will be x1 plus x2 plus x3, 0, 0, y1 plus y2 plus y3. Final answer will be this, right? And next one, right? So this is the, if you consider the RHS also, A plus B you have to add, then C. A plus B is nothing but x1 plus x2, y 0, 0, y1 plus y2. Then you are adding with C, x3. So finally what you get? So this is the thing, right? So A, x1 plus A plus B is this part. C is this, right? C is this part. Then sum of this is x1 plus x2 plus x3, 0, 0, y1 plus y2 plus y3. Okay. So you can observe that left hand side is equal to the right hand side. So the second part is proved. Okay. The third one is this. So the third one is zero vector. And as you all know, in a particular vector, zero vector is for a matrix, zero vector is 0 0 0 only. You had 0 plus a, you should get a, right? Zero vector is 0 0 0. You're adding with the vector a, x1 0 0 y1. What you get is, when you add with the 0, you'll get the x1 0 0 y1 only. So 0 plus a is a. Third is proved. Whereas the fourth one is you have to find the vector such that you should add it with the vector a such that you should get zero vector, right? So vector a is x1 0 0 y1. If you add minus a, you will get 0, right? So you have to add with minus x1 0 0 minus y1. So after adding, what you get is 0 0 0 0, right? So minus a you have to consider in order to prove the fourth one, right? Then so with respect to the fifth one, right? So you're in the fifth one, condition is ia, right? So you have to find the identity value. When you multiply with the a, you should get a. So in the matrix, it's identity matrix 1 0 0 1. You multiply with x1 0 0 y1. Definitely you should get that a, x1 0 0 y1. Okay. And next, the sixth case is this. You are considering two constant. The actual formula is this: c1 c2 into x is equal to c1 times c2 into x, right? So let's consider the LHS. c1 c2 into a is x1 0 0 y1. So after multiplication, what you get is c1 c2 x1 0 0 c1 c2 y1, right? So then what you should do, is this. So we multiplied, this is LHS, okay? So next part is RHS. So this part, this is RHS. Again, we are considering that. So what we are doing is we are calculating C2A. So multiplying the constant C2 to the A. A is x1 0 0 y1. So if you multiply with C2, you'll get C2x 0 0 C2y. Then you are multiplying with C1. Finally, you'll get this. So when you compare LHS and RHS, both are equal, right? So sixth one is also proved. Okay. So, and the seventh one, you can see that. So this will be C1 times of A plus B is equal to C1A plus C1B, right? So you have to calculate first A plus B. So A is x1 0 0 y1, B is x2 0 0 y2, right? So what you get is x1 plus x2 0 0 y1 plus y2. Then you multiply with C. Finally, what you get is C1 times x1 plus x2 0 0 C1 times y1 plus y2. So similarly, you can prove the right hand side. So both are equal. So, and eighth step, that is C1 plus C2 into A is equal to C1A plus C2A. C1 plus C2 into A is what? X1 0 0 y1. Then what happens? So C1 and C2 you should multiply individually, or you can multiply together. So you can see the left hand side here, right? From this point, I have taken directly this LHS. So multiplied C1 C2 into x1 0 0. When you multiply constant with the 0, you'll get that 0 only. Here the RHS is this. So you consider the RHS part, C1 into x plus C2 multiplication. C1 into A, if you multiply, you'll get C1 x1 0 0 C1 y1. If you multiply C2 with the B, that means A only. That means what you get is C2 x1 0 0 C2 y1. After you adding, LHS becomes RHS, right? After you adding, C1 x1 will add to C2 x1, 0 will add to 0, this 0 will add to 0, this will add to this. So finally, this is the answer. LHS is equal to RHS, okay? So all the axioms of the vector space are satisfied. So V is a vector space over the field of real numbers. So V is a vector space of real numbers. Okay. Since all the cases are satisfied, all the 8 rules are satisfied, you can call that particular V, which is x0 0 y, is a vector space. Okay. Next is this. Next problem. Show that set of all integers is not a vector space. Okay. So you are considering all integers. Okay. So one of the main, in order to show that it's not a vector space, out of those 8 axioms, you can prove one. If you prove that one is wrong, then you can conclude that it's not a vector space. It's left to you which one to choose. So to show that a set is not a vector space, you need to find only one axiom which is not satisfied. Okay. So here all x and y's are integers. So you have to show that set of integers is not a vector space. So let's consider a vector. One is an integer, right? Assume that it belongs to V. Then you have a constant. Consider a constant 1 by 2. Then it's a real number. When you multiply 1 by 2 to the 1, right? It becomes 1 by 2. So since 1 by 2 is not an integer, see, as you all know, vector space, when you multiply with the constant C with V, the answer should lie in that vector space only. So CV, after multiplication of C and V, you get 1 by 2. That is not there in set of integers. So that's why it is not a vector space. C, you can consider all the possible, you can consider C as 1, 2, 3, anything. You can prove that, it's a vector space. You should not do that way. You find out only one point, weak point, where it disproves. That you should find out. Okay. You can prove in the other way, but actual truth is, it is not valid for all the cases. You have to find the case where it disproves the proper thing. Okay. So here what happened is, we considered as a set of integers. So in the one of the axiom was C into A should lies in the vector space. So C I considered as a real number 1 by 2. The V is a integer only 1. After that you got 1 by 2. So that's why it does not belongs to V. So that's why what you can call is, it is not closed under scalar multiplication. It is not a vector space. Okay. So this result 1 by 2 is not comes under that set of integers. That's why the word, it is not closed under scalar multiplication. Okay. So that is the second problem. The third problem is this. Third problem is, the set of all second degree polynomial function is not a vector space. Set of all second degree polynomial. That means you are considering in the set, you are considering only second degree polynomials. What are the examples of second degree polynomials? It's x square plus 1, x square plus x plus 1, x square plus x, 2x square plus 3x plus 4 is equal to 0. These are all second degree polynomials. You are considering only the set of second degree polynomials. Okay. And you have to prove that it's not a vector space. That set, you have to prove that it is not a vector space. So you can assume whatever the question. See, why, sir, you have assumed only x square only? It's your wish. You can choose whatever you want. And you try to do it on your own way. Then only you'll understand. Okay. You take y square, z square, whatever you want. Okay. It need not be the common always. P of x. So here I am considering P of x is equal to x square. Two polynomials. Polynomial is represented by P of x, function of x. Okay. P of x. Generally you'll write as f of x. Here it is a P of x. Is x square. One is this. And another one is g of x. It is minus x square plus x plus 1. Okay. Two polynomials I have considered. And you have to consider such a way that you should prove that it's not a vector space. Okay. You have to find the weak link. You can consider x square plus 1. Here I want to disprove that, for this condition it won't work. That condition only you should pick. X square minus x square plus x plus 1. One is x square, another one is minus x square plus x plus 1. One is P of x, another one is g of x. What I'm doing is, I'm adding those two. And as you all know, the first property is that x plus y, if you take any two vectors, if you had, the result should also lies in the vector space only. Here when you add it, what happens is, you're adding px and gx. When you add it, x square minus x square plus x plus 1, my x square minus x square will cancel. You're left with only x plus 1. That is not a second degree polynomial. Correct? No, x plus 1 is not a second degree polynomial. So that doesn't belongs to set of all second degree polynomial. After adding two functions, P of x and g of x, the result x plus 1 is not in that set of second degree polynomial. Okay, that's why it's not closed under vector addition. It's not a vector space. Okay, so it's not a vector space. So what was the expectation was the resultant, if you would have got as second degree polynomial instead of x plus 1, if you have got x square plus 1, then you can consider, it is closed under vector addition, you can call it as like that. But here you got a single degree equation. But the trick is you should find this kind of function only. See, if p of x is x square, g of x is x square plus 1, then you add, you'll get 2x square plus 1. You should not conclude that, it's a vector space. You have to find the g of x. You have to use your mind to find out the weak link of it, right? Where it will disprove. Okay, you always try to think in that way. The fourth problem, okay, let v is equal to x comma y. Okay, so vector v, set of vector v is x comma y. It's a 2 coordinate system, x comma y. And what is the condition for x and y? X is greater than or equal to 0. So x has all the positive numbers plus 0 is there. Y is also greater than 0. That means it has all the values including 0, positive values including 0. With standard operation, is it a vector space? That is the question they are asking, right? So you can always take examples and you can prove it. Okay, that is also there. It doesn't mean that always you should not express in terms of a general terms only. Like that, the first problem what we did. Okay, you can take simple example. Let's consider x comma y as 1 comma 1. So what is the condition of x and y? X should be greater than 0, greater than or equal to 0. Y is greater than or equal to 0. Correct? No. So that's why I chose x and y as 1 comma 1. So both x and y are greater than 0. What I am trying to do is I'm multiplying with c of x comma y, right? Fifth or sixth property, right? So when you multiply with the constant to the vector cx, that should also comes in that the answer after multiplying with the c, the answer should also come in that set of vectors only, right? Suppose if you have a set of vectors like 1 1 2 2 3 3, when you multiply the constant 1 1 with 2, the answer is 2 2. That is also in the vector set of vector, like that it is. So here I'm considering c is minus 1. C is a real number. Okay, there is no condition for c. C is a real number. Intentionally I am taking as minus 1. So x comma y is 1 1. When you multiply minus 1 with 1 1, you'll get minus 1 minus 1. But what is there? The resultant is minus 1 minus 1. That is not greater than 0. Correct? No. Here resultant is minus 1 minus 1. Both are not greater than 0. So that's why it is not belongs to this v, right? What is the v? It's a x comma y, right? X greater than 0, y greater. That this vector does not, minus 1 comma 1 does not lies in that vector, right? So it is not a vector space. Okay, fifth problem. Show that the set of non-singular 2 cross 2 matrix is not a vector space. What is the meaning of non-singular, singular and non-singular matrices? If the singular matrix, if determinant is 0 for that matrix, then it is called a singular matrix. If determinant of the particular matrix is not equal to 0, then it is called a non-singular matrix. Okay. The question is, show that set of non-singular 2 cross 2 matrix. So it is a 2 cross 2 matrix and it is non-singular. The set is set of so many non-singular matrices. What is non-singular? If you calculate determinant of all the 2 cross 2 matrix which is in that set, it's not equal to 0. Show, and you have to show that this set of non-singular matrix is not a vector space. And one more condition. Show also that set of singular 2 cross 2 matrix is not a vector space. So you have to prove two things. One is set of non-singular matrix as not a vector space. Another one is set of singular matrix is not a vector space. Two things we have to prove, right? Here, the thing is, so sum of two non-singular matrix. I'm considering randomly two non-singular matrix. So matrix A is 1 3 5 6. See, you can choose whatever you want, okay? But the condition is after finding the determinant, it should not be 0. See, You calculate the determinant of A, 6 into 1 minus 5 into 3. So 6 into 1 is 6, minus 5 3 is 15. 6 minus 15 is minus 9. So determinant is not equal to 0. You calculate determinant of this, minus 4 minus of 3. So minus 1. So it's not equal to 0. So I'm considering two cases. You have to choose such a way that you should get a singular matrix, because after addition also, after adding two non-singular matrices also, result should also be a non-singular matrix. Then only it is called as a vector space. Here you have to prove that it's see, A plus B, right? Here you are adding A plus B. What is the answer you get? 1 plus 1 is 2, 3 minus 1 is 2, 5 minus 3 is 2, 6 minus 4 is 2. You calculate the determinant of this. 2 into 2 is 4, minus 4, it's become 0. So after adding non-singular matrix, you are getting a singular matrix. So that is wrong, correct? No, after adding non-singular matrix also, you should get the non-singular matrix only. Then only you can call it as a vector space, right? So you have to carefully choose these numbers so that you should get the singular matrix, right? So that is left to you. Okay, you should choose properly. Then you can prove that since you calculate the determinant, so sum of two non-singular matrix is a singular matrix. That is with respect to example. So that's why it's not a vector space. Similarly, you consider, okay, here in this case, the next proof what you should do is you have to consider two singular matrix, right? So one of the matrix A is 1, 2, 3, 6. Okay, you calculate the determinant of this, 6 minus 6, it's 0. Here B matrix, you calculate the determinant of this, 2 minus 2, it is 0. So both are singular matrix. Now what you should do, you should add, right? A plus B you add. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 6 plus 2 is 8, correct? No, so now you find the determinant of this, 2, 3, 5, 6. What is the determinant? 2 8s are 16 minus 15, it's 3. Actually, after adding two non-singular matrix, you should get the result also as a singular matrix. But here the answer is non-singular. So that's why it is not a vector space. Both the set of, see in that set, I'm considered only, see where is the set, sir? Questions bandra. You have to consider, you have to assume two vectors. Okay. So I have considered I have assumed that two vectors here, right? Two singular vectors, singular matrices, and I try to add the resultant I'm expecting as a singular matrix only, but what I got was non-singular. That's why it is it's not a vector space. Okay, this question you try to understand properly. Okay, this is from the prescribed textbook. Okay, yeah, first question. Okay, suppose addition in R square. Okay, R square is nothing but what? Two dimension is nothing but x comma y coordinate should be there. Okay, addition in R square adds an extra 1 to each component. It's not regular addition. Okay, so after adding, you should add one more number to it. That is how they are defining. See, this is the definition of the vector space. Okay, you may not you should not tell that, see, two vectors are considered here, 3 comma 1 and 5 comma 0. Actual answer is after adding you should get 8 comma 1, but here what they are defining as a vector, once you add, then you add again extra 1 to each component. That is what they are saying. So actually, according to the definition, when you add these two vectors with respect to this set only, okay, it's not generalized. So with respect to this set, so 3 comma 1 and 5 comma 0 you're adding, what you get is 8 comma 0, but 8 comma 1, you should supposed to get 8 comma 1, but according to the definition you are adding one more for both 8 and 1. What you get is, when you add 1 to 8 you'll get 9, when you add 1 to 1 you'll get 2. So 3 comma 1 and 5 comma 0 is 9 comma 2. Let's consider one more case, like 1 comma 1 and 2 comma 2. What is the answer? It is 4 comma 4. It's not 3 comma 3 according to this definition. With scalar multiplication unchanged, that means the scalar here they have changed the addition, but scalar multiplication remains unchanged. That means if you multiply 2 to 3 comma 1, it will be 6 comma 2 only. That is what they mean. which rules are broken. That means what they're pointing out is all the 8 rules are there, no? So in that 8 rules, which are all broken with this condition, you have to find out. Next question is this. Okay. Yeah, we'll try to solve this question first. Yeah. The first question is that addition and scalar multiplication are required to satisfy 8 rules. That is that since we change operation of addition, we are looking for rules that are related to the addition. Since there is no change with respect to the multiplication, you are to look for only the addition part. So let's consider x plus 0. That is the rule, right? Rule 3 is x plus 0. You should get x. But here what happens? You consider x as x1 comma x2. That is 3 comma 1 or something. Then you consider vector 0 0. What is the answer you get is, instead of x comma x2, according to the definition which is given earlier, what you get is x1 plus 1, x2 plus 1. But what is the expected answer? X plus 0 should be x, right? X plus 0 should be x. But here what you are getting is x plus 0, you are getting something else. So that's why, this is one of the rule which breaks when you change the addition. Okay. And rule number 3 is also broken. Yeah, rule number 3, we looked for the rules that do not, this is your mindset. Okay, this should be your mindset. You should look for rules that do not have the same number of addition on both the sides. If you look for those kind, in x plus 0, you have in the left hand side you have addition, one addition, right hand side you don't have. So you'll not get the proper answer for this. Those kind of things you should look for 8 rules. You should not take the first condition, a plus b is equal to b plus a. Even if you do that, it proves, okay, it will be okay for this condition. You have to take the third one basically because in the left hand side you have addition x plus 0, in the right hand side it's only answer x. So that's why we choose that. Let's try to understand the second question. Okay, second question is this: show that the set of all positive real numbers with x plus y and cx redefined to equal the usual xy and x of c is a vector space. What is the zero vector? What they mean to say is, show that, okay, you have to show set of all positive real numbers. That means, you have a set of all positive real numbers, okay, with x plus y and cx. Right? We used all these things in all the 8 exams. We used x plus y and we multiplied a constant with the x, right? Some of the exams are there. You have to redefine it, okay? You have to redefine it. What is the redefined thing? Instead of x plus y, you should use xy. Instead of cx, you should use x to the power of c, okay? So then you tell me, after replacing this, instead of x plus y, you should replace as x into y. Instead of cx, you should replace by x to the power of c. After replacing, whether it is a vector space, that is their question. Okay, whether is it a vector space after replacing it, and you have to find out what is the zero vector. Okay, so answer is this. You can observe very carefully. Right? The first one is this. What was the first one in the axiom? It was x plus y is equal to y plus x. But here in the question, what they're telling is you have to replace plus by multiplication. So what you get is x y is equal to yx. So in the real numbers, set of real numbers, x into y is y into x. Correct? No. 1 into 1 by 2 is 1 by 2 into 1. Both are equal, right? So that is proved. Second one is this, right? The second condition was associative property. X plus y plus z was there. That is equal to y plus x, and that means x plus y plus z was there previously. Now everything is replaced by multiplication. That is also proved. Here zero vector is a trick. In the zero vector, what we did was, during the addition, it was 0 plus x. You get x. Since it's a multiplication, see, zero vector concept is what? When you add something to that vector, you should get back the same vector. When you add some vector to the zero vector, you should get back the same vector. If you add x vector to zero vector, you should get back the x vector. Here, since it's a multiplication, you should multiply with 1. 1 is a zero vector because when you multiply anything to the 1, you get back the same thing. When you multiply x to the 1, you will get back the x. That's why 0 vector is 1 here, since it's a multiplication. And in the previous fourth step, what we did was like,
Sir,
uh,
sir, is this a problem or property, sir?
problem.
Okay.
This is how you'll get the problems. Okay. They'll ask that kind of questions only. Okay. It's a problem only. You have to prove like this. Okay. Here, the fourth one is this. Here, like previously, what we did was like x minus x we took and it becomes 0. Here, 0th vector is 1. Okay. Here, in this case, 0 vector is 1. So you should get back the 0 vector. That is the concept of this inverse. You should get back the 0 vector. 0 vector is 1 here. So inverse should be 1 by x. Okay. The fifth one is this. C into x was no, I into x was there, right? In the first condition, whatever I told. Here, cx should be represented as x to the power of c in this question. So I into x becomes x to the power of y. Okay. So that means x to the power of 1, it becomes x. Here, the next condition is in the sixth condition, previously it was c1 into c2 into x was there. Here, cx is nothing but x to the power of 6. So all the constant comes above x, power of x. X of c of c1, c2, that you can write it as x of c1 times c2. So obviously you know that x to the power of square, all to the power of square is nothing but x to the power of 4. You can multiply easily, right? So this is nothing but x, y. So previously it was c into x plus y. So c you should put it in rise to the power. Instead of plus, you should write the multiplication. That you will get like this. This is also proved, correct? No, both are one and the same, right? You substitute some value for it, x and y. Substitute x is equal to 1, y is equal to 2. Substitute c is equal to 2. That is nothing but 1 to the power of 2 plus 2 to the power of 2, right? X is 1, y is 2, c is 3. What happens then? 1 to the power of 3 into 2 to the power of 3. That becomes 2 to the power of 3. The same answer you will get left hand side and right hand side for the real numbers. Okay. So that is also proved. And here also in the eighth one, x to the power of c plus c1 plus c2. So previously it was c1 plus c2 into x. So here you have to write like this. So set of all. So what is the conclusion? Set of all positive real numbers with the given operation is a vector space. So even though you replace addition with the subtraction with respect, addition with the multiplication and multiplication of the constant to the rise to the power of that particular variable, after changing with respect to the real numbers, it is true. Okay.
Sir, in fourth property, it should be 0, no, sir, if we take the inverse ones.
Oh, no. See, what is the inverse zeroth vector?
No, sir, in addition property, when we took x and x inverse addition.
Yeah. See, in addition, what you did was, what is the inverse for addition? The minus of that. Correct now?
Yes, sir. Yes.
If you take 2, see, you should find a inverse vector such that you should get the zeroth vector. That is the condition, fourth condition. See, in addition, you consider 2 number. The answer should be zeroth vector, 0. What is the inverse vector of 2? It is minus 2, right? You'll get 0. But in multiplication, what happens is, zeroth vector is 1, correct? No, zeroth vector is what? See, 0 anta ಬಂದ ತಕ್ಷಣ 0 ಇರಬೇಕು ಅಂತ ಏನಿಲ್ಲ, right? Zeroth vector is nothing but
then we can say that it will not satisfy, no, sir.
So how do I convince you? Okay. See, what is your query here? Fourth one, what is your query?
Sir, if we took inverse means it should be 0 according to our main formula, sir. So here we are not getting that term, sir, 0. Hence we can say that it is not satisfying all the real numbers.
No. What inverse you want to take?
Sir, in fourth property, according
with respect to multiplication, you tell. Yeah, addition minus x, it's fine. What with respect to multiplication?
Sir, then when we'll take with respect to multiplication, we should see that it should come as 1.
Oh, yeah. you should choose the inverse such a way that whether that inverse exists in the vector, that is the question. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಈಗ ನೋಡು x ಅಂತ ಇದೆ, ಅರ್ಥ
Yes.
ಆಯ್ತಾ? I have to find out something, you should get back 1.
Okay.
So how to get back 1 with respect to x when there is a multiplication? You should write 1 by x. Okay. Suppose x na 2 anta itko.
Yes.
So 1 by x is what? 1 by 2. Whether 1 by 2 is in real number?
Yes,
It
sir.
is there.
Yes.
So 1 by x exists in the real number. So always for any number you consider in the real number, okay?
Yes,
so it becomes this condition. Okay now?
Then we should consider that with respect to multiplication, it should be always 1, and with respect to addition, it should be 0.
Yeah.
Okay.
Yeah. See, it will change with respect to everything. If it is a matrix, if you consider what is a inverse matrix, A inverse you should write. Like that it is. A matrix, if you consider A inverse is I, right?
Yes, sir.
Zero vector is identity matrix there in matrix. When you multiply any vector x with the identity matrix, you will get x. No, that's why I is zero vector with respect to multiplication. I am telling. Okay.
Okay.
With respect to addition, it is zero vector only.
Okay.
And for suppose if it is a matrix 1 2 3 4 is there, then inverse of that matrix is -1 -2 minus x only. The same thing will come. Okay. Yeah. Third one we'll see. Okay. I'll take another 5 minutes. Okay. Yeah. Suppose x plus y1 comma y2. Two vectors are there. Okay. Two-dimensional vectors. A comma b and two vectors you are considering. See, you have to imagine the two-dimensional space. Okay. 1 comma 2, 3 comma 4, like that. Two vectors are there. In the question, what they are doing is they are adding. Okay. And what is the actual answer? When you add it, you will get x1 plus y1, x2 plus y2. That is what answer you should get. But here what they are defining is x1, x2, y1, y2 as this. What is the changes? You are adding the first x1 to y2, x2 to first, second vector first term. So x2, y1, x1, y2. That is how they are defining. Okay. So they're defining like this. With the usual, Cx is not changed, just like the first problem. Okay, Cx is not changed. That means multiplication of C into x is nothing but C into x1, x2 is nothing but Cx1, Cx2 only. C into y1, y2 is nothing but Cy1, y2 only. So there is no change with respect to the multiplication. Only change is addition. Here x1 is the first term, first element of the vector 1 is adding with the second element of the vector 2. Second element of the vector 1 is adding with the first element. That is how they are defining. Okay, addition. Which of the 8 conditions are not satisfied? Here I have taken only one condition. So many conditions are not satisfied here, but I am explaining with respect to only one example. Here you consider. Okay, so when you consider this, so actual example is this. That is how they are given. Okay, x comma y, x1 comma x2 plus y1 comma y2 is nothing but x1 plus xy2 and x2 plus y1. This is what they are given. So rule 1 is this. This is what they are given in the question. Okay, rule 1 is this: x plus y is equal to y plus x, commutative law. Now you do that. Take the left hand side. Okay, now what happens here is, now you try to do this is LHS what you got. So after adding this xy plot, here they are done. Okay, this is LHS. The second term is RHS. RHS is what? Y plus x. Okay, RHS is y plus x. What is y? Y1, y2. What is x term? X1, x2. After adding, what you get is y1, the first element will be added to the second element of the second vector. That means y1, x2 will come, and the second element of the first vector will be added to the first element of the second vector. Y2 plus x1 will come. Okay, so when you compare LHS and RHS, they are not equal. In the first case it was x1 plus y2. The second case it was y1 plus x2. Right? See, in the vector ಸರ್ ಅದೇನು ಸರ್ ಎರಡು ಎಕ್ಸ್ಚೇಂಜ್ ಸರಿ ಇದೆಯಲ್ಲ ಹಂಗೆ ಹಂಗೆ ಅಂತೆಲ್ಲ ಥಿಂಕ್ ಮಾಡಬೇಡಿ. ಯರ್ ದ ಥಿಂಗ್ ಇಸ್ ಸಿ 1, 2 is entirely different from 2, 1. Correct? No, in a vector 1, 2 here x is 1, y is 2. Here 2, 1 the position only changes. 2 is y, 2 is x, and in 1, 2 x is 1. In 2, 1 x is 2. So the position changes. So they are not equal. Okay, that you should know. So since they are not equal, you can call that. Okay.